This course is called the finite element method. In this course, we are going to develop a mathematical tool with which we are going to study boundary value problems and or initial value problems of mathematical physics. For us engineers, this tool has to be used in all stages of an engineering analysis. The physical problems that we face in everyday engineering are many. For example, let us take a physical phenomenon which can be the bending of this pen. This pen is fixed at one end, I am holding it on with my fingers, and at the other end I am applying a load. This is a three-dimensional object subjected to a loading which I am showing here, and under the action of this loading this pen bends. This physical phenomenon is generally modeled using a generalized mathematical model. The generalized mathematical model will incorporate all the essential features of the physical state of the system. Now, in principle and in practice, one would not like to solve the most general mathematical model because the problem then becomes almost intractable. So, one would like to simplify the problem and pose a so-called simplified mathematical model. As soon as we go from the generalized to the simplified mathematical model, we commit something called a modeling error. This modeling error should be sufficiently small so that the physics that we are after is reasonably accurately predicted by our simplified model. Now, for the simplified model, we have to obtain a solution. Unfortunately, in engineering practice, again let us look at this pen. This is quite a complicated geometry, and we cannot obtain the exact solution to this simplified problem in the most general case. So what we would like to do is obtain an approximate solution. A tool to obtain the approximate solution is the finite element analysis. Now, once I have obtained an approximate solution, then the analyst has to decide whether that approximate solution is good enough or not for his engineering decisions to be made. If he thinks that the approximate solution is good, then he accepts that and then starts post-processing the solution, i.e. obtaining response quantities of interest. For example, for this beam, that is my pen, I may be interested in the tip deflection at this point here, or I may be interested in knowing what is the stress distribution in the beam, so that I can decide whether the pen is going to fail at any point of interest. For example, in this case the pen may fail at the root. So once I have obtained these response quantities of interest, then I am going to, as an analyst or as a designer, I am going to make certain engineering decisions, i.e. whether my design is good or I have to make certain modifications. For example, if I see that this pen under the action of this load hardly does anything, that is, it is absolutely safe, then I may decide to remove material from the pen. That is, I will make geometric changes to the pen. That is, here I am going to change the geometry or make the pen thinner. In certain cases, for example, in aircraft engineering applications, I would like to keep the geometry fixed. For example, the wing of an aircraft. Wing is given a certain geometrical shape so that it can develop the required amount of lift. In that case, I cannot change the shape, and I find that under the action of the aerodynamic loads, which can be represented again like a beam under the action of transverse loads, the wing bends too much. It is unsafe. In that case, I will have to either change the material that I have used in the wing, or I will have to enforce the material inside the wing. That is, I have to add stiffeners inside the wing. After I have done all those things, then I will look at my final design and decide as a designer and as an analyst whether this design is acceptable. So this is an iterative process, and the solution obtained using a finite element analysis at every step of the design process gives us the response quantities that we are looking for, so that I can make my engineering decisions. So once this job is done, then I approve the design and send it for prototype fabrication. After the prototype is made, then laboratory tests have to be done to see whether what I have done is good or not. If it is not good, then I have to go back to the drawing table. So let us now look at a few typical simplified mathematical problems that arise in everyday engineering practice. For example, we have this figure here which represents a bar, slender member, with variable cross section, a bar with variable cross section here, subjected to an axial force which is a distributed body force Fx, a point load at point x naught of size f, an end load P, and it is constrained at the point x equal to 0. It is constrained here. Under the action of these loads, I would like to now obtain the deformed shape of the bar. I would like to know what happens to this bar. So let us now give the differential equation which corresponds to the state of the bar. So under the action of the load, the bar is going to deform as such: d dx of E ax du dx plus fx is equal to 0 for 0 less than x less than L. That is, for every point inside the bar, this differential equation has to be satisfied. Okay, that's not all. When we are talking of a boundary value problem, then we have to also talk about the point x naught, where I have applied a point load. At the point x naught, what happens is there is a jump in the axial force. So Ea du dx at the point x naught minus Ea du dx at the point x naught plus is equal to f. This also has to be satisfied. Further, at the end 0, x equal to 0, I will have my displacement is equal to 0, and at the end L, I will have force Ea du dx at end x equal to L is equal to P. This is the complete boundary value problem corresponding to the bar. Look here that we have a variable cross section. So in this case, if I try to solve this problem exactly, I cannot obtain the exact solution by hand. In that case, I'll have to resort to an approximate solution which will be provided by the finite element method. So let us now look at another boundary value problem of interest, which corresponds to the pen that I was holding earlier. This is a cantilevered beam subjected to a distributed load Qx, it's a transverse load, and an end bending moment M given by this arrow. This bending moment is acting about the z-axis, and this beam, under the action of these loads, it is going to bend. So the deformation of the beam will be given by a corresponding differential equation, which is d2 dx squared E Ix where EIX is nothing but the flexural rigidity of the beam at a point X, d2W dx squared, where W is the transverse deformation of the beam. This is equal to the Qx that is applied. This is true for all points lying between 0 and L. Now let us look at the boundary conditions. In this case, the boundary conditions are W at 0, because I fixed the beam at 0, is equal to 0. Further, because it's a cantilever beam, the rotation at the point 0 is also set to 0. This is the boundary condition at the point x equal to 0. Similarly, at the point x equal to L, we have an applied bending moment. So I will have EI d2W dx squared at the point x equal to L is equal to m. There is no shear force at the end, which is a free end as far as the shear force is concerned. So I will have minus d dx of EI d2W dx squared at x equal to L is equal to 0. So under the action of the given distributed load with the given constraint at the point x equal to 0 and the end bending moment and the 0 shear force, this beam deflects. This is another simplified problem that we will be interested in. So now we have posed certain simplified boundary value problems that we will be looking at during the course. Let us also see what are the objectives of this course. So as far as the objectives are concerned, we are going to go in a step-by-step manner, starting with the development of the finite element method using a one-dimensional model problem. For the one-dimensional model problem, we are going to take the variable cross-section bar that we have drawn earlier. Then, for this model problem, we are going to pose the finite element method or the finite element formulation, obtain a solution, and we will show how we can refine the solution. That is, how we can improve the quality of the approximate solution that we have obtained. Once we have done that, then we are going to develop the framework of a one-dimensional finite element program, which can be programmed by the students, and we can actually get the deformations, stresses for a bar subjected to various kinds of axial loads. This is what we are going to do as the third part of the course. Then we are going to extend whatever we have done to other one-dimensional boundary value problems. For example, we have already drawn the beam. We will look at the beam. We can look at heat conduction problem in a bar, or we can look at one-dimensional fluid flow, etc. Many problems of that kind can be tackled, and we will show that we do not have to do significantly different things in order to tackle these problems. Once we have consolidated our fundamental knowledge of what the finite element method and the finite element analysis is, then we will go to the two-dimensional boundary value problems, where we will start with a simplified steady state heat conduction problem, for which we will develop the full framework of the finite element formulation. From there, we will go and develop a simple. In this case, we will not be too detailed in what we do. We will develop a simple two-dimensional finite element program to solve the two-dimensional problem. Once we have developed the program, then we will extend our formulation to cover problems of planar elasticity. For example, plane strain or the plane stress problem. For this, we'll also outline how to develop the finite element program. Now, once we have finished the two-dimensional problem, then we'll look at certain other special problems which are very important to an engineer. For example, we may be interested in the free vibration problem of a continuous system, beam vibration for example, which is nothing but an eigenvalue problem. Or we'll be interested in the dynamic response of a bar or a beam or a plate under the action of time varying loads. Then we'll have to develop the formulation for a time dependent problem. Further, we may be interested in problems which are nonlinear in nature. For example, geometric nonlinearity can be incorporated in our formulation. So this is essentially what we are going to cover in this course. So once we have outlined the objectives of the course, let us now look at the basic steps which are involved in a finite element formulation. So what are the basic steps? We will highlight the basic steps using the one-dimensional problem. Let us take the bar. In that case, the bar is a domain extending from the point x equal to 0 to the point x equal to L. This bar we are going to partition into smaller pieces. By putting these extra points in the domain. These will be, I can put them with size h1 here, h2, h3 and h4. When we partition the domain, which is an interval of size 0 to L, the domain we will call by omega, which is equal to the interval 0 to L. This domain will be partitioned into smaller subdomains, which are omega 1, which is equal to 0 to h1, omega 2, which is equal to h1 to h1 plus h2, and so on. The smaller subdomains are given a name in the finite element analysis. These are called elements. So in this case, we have these 4 smaller subdomains which together form the full domain. So we have 4 elements in this case. So the 4 elements are omega 1, omega 2, omega 3 and omega 4. The nodes that we have placed, or the points which basically form the boundaries of each of these domains, are called the nodes. So this point will be a node. So in this case, if you see, there are 4 elements and we have 5 nodes, 1, 2, 3, 4, 5. So we can draw a figure here and have the node corresponding to point x1, node corresponding to point x2, node corresponding to point x3, node corresponding to point x4 and node corresponding to point x5, which for us here is L and x1 is 0. So once we have the elements and the nodes, then the next step is to now define functions over these elements. By the way, the process of forming the elements and nodes is called meshing. So that process was meshing. That was the first part of any finite element analysis. So once I have made the mesh, then over these nodes I am going to define functions. How do I define these functions? These functions will be such that, let us take the first node. So I will call this function phi1, which is linear in the element 1, which is linear in omega 1, and it has a value 1 at the node 1 and 0 at all other nodes. So what will that function look like? will look like this. So I can draw the area under that curve. So this is my function phi 1. So what I'm going to do is I'm going to construct these piecewise polynomial functions which are continuous in the full domain and which vanish at certain nodes and take a value 1 at a particular node. So let us take any generic node I and its two neighboring nodes I minus 1 and I plus 1. So if I now define what is phi corresponding to the node I, then the phi will be this function. Such that it has a value 1 at point I, and at point I minus 1 and at point I plus 1 it is 0, and I'm going to extend it in the full domain with the value 0. So if I have elements here, this function will have a value 0 everywhere else. These functions phi i's corresponding to the nodes. So in this case, if I go back to my mesh that I formed, there will be 5 such functions phi I. These functions phi I are called basis functions. So once I have the basis functions, then in terms of the basis functions, I am going to define my finite element solution. So U finite element x is equal to sum over I is equal to 1 to 5 in our case, ui phi I x. These ui's are the unknown coefficients which we have to obtain using the finite element method. So once I have obtained these coefficients ui, then I have the full finite element solution for any point in the domain 0 to L. So let us now take our problem again and draw the various global functions phi I that we have. So the first phi I, so this is node 1, node 2, node 3, node 4, node 5. The phi I, this is phi 1, which extends to 0 everywhere else. This will be phi 2, which will extend to 0 everywhere else. Similarly, phi 3 will be 0 here, 1 here, phi 4 will be 0 everywhere up to node 3. Beyond node 3, that is in element 3, it is non-zero, linear. At node 4, it is of size 1, and at node 5, it comes down to 0. Similarly, the last one will be phi 5. And this phi 5 is extended to 0 beyond node 4. So these are our phi functions. These are also called hat functions. So these are nothing but hat functions. Now, if you see something about these hat functions, what is happening? Each of this function is non-zero only in certain elements. If you take, for example, phi 3, it is non-zero only in element omega 2 and element omega 3, while it is 0 everywhere else. Such functions which are 0 in most of the domain and non-zero in only a small part of the domain are called functions with local support. this is a very important feature of the finite element method, in that for the approximation we are using functions which are only defined in a small part of the domain, and by piecing up these functions we construct the approximation over the full domain. Okay, now let us see how we are going to obtain the coefficients of the finite element solution. If you remember that UFE was summation of ui phi I. So we have to still find a way by which we can obtain the UIs. So that brings us to the next step of the finite element method, which is called element calculations. So this part is element calculation. What is the idea? If you take an element omega I, so it will have nodes I and I plus 1. So in this element, which of the phi i's are going to be non-zero? So the only phi i's which are going to be non-zero are going to be phi I and phi I plus 1. These phi i's in the element are given a name. The name is n1 of element I and n2 of element I. This n1 of element I and n2 of element I are called element shape functions. So you have to understand that the element shape functions are nothing but the part of the global basis functions phi i's which are non-zero in the element I. This way we will have the shape functions for each of the elements. So what we are going to do next is, if I look at the finite element solution in this element I, so U finite element in element I, in element omega I is equal to, what will it be? It will be equal to ui phi I plus ui plus 1 phi I plus 1, which can be rewritten in terms of the element shape functions as ui n1 of I plus ui plus 1 n2 of I. And as we will see later on, the equations from the element corresponding to these unknown coefficients ui and ui plus 1 can be obtained through the finite element formulation, and what we will end up getting at the element level are a matrix Ki and a so-called load vector Fi. So for each element, this matrix will be in terms of the two unknowns ui and ui plus 1, and the Fi will also correspond to this ui and ui plus 1. So for each element I am going to obtain this set of, in this case for example, if I take this problem, two equations or contributions to two equations corresponding to the ui and ui plus 1. So the next job is assembly of these equations. So once I have obtained these element level equations for each of these elements, so for the first element I will get the equation corresponding to u1 and u2. For the second element I will get the equations corresponding to u2 and u3. For the third element I will get the equations corresponding to u3 and u4, and for the fourth element I will get equations corresponding to u4 and u5. Then the question is, how do we bring these equations together to give us 5 equations in terms of the 5 unknowns u1 to u5. So that process is called assembly. Here we will add up all the element equations to obtain a so-called global matrix K, such that K into U, where U is a vector of size 5, it will have the unknowns U1, U2, U3, U4 and U5. This will be equal to a vector on the right hand side called F. These things are also given names. K is called the global stiffness matrix. U is called the displacement vector. And F is given the name of the load vector. So this sounds very much like civil engineering, where we have a truss or a matrix structure, or we can think of this like a spring mass system, where K represents the stiffness, U represents the displacement of every mass, and F is the applied force, the vector of the applied forces at the various mass points. So this equivalently becomes a system with stiffness K and subjected to an external load F. So once we have done the assembly, our job is not over. If you remember that nodes 1 and 5 have something special specified at them. For example, at node 1, I may have the displacement given a particular value. It is given a value 0. And at node 5, I will have the force, for example, is equal to the applied force P. So this has to also be incorporated into our equations. So what we do next is called application of boundary conditions. That is, we enforce the conditions at the end x equal to 0 and at the end x equal to L for our problem that we have taken. Once we enforce the boundary conditions, it is going to show up in terms of modification of the stiffness matrix and the load vector F. Finally, we have the system of equations corresponding to the 5 unknowns that we have posed in this problem. You can have 10 unknowns, n unknowns. So I will have n equations in terms of the n unknowns which we are going to solve. And n by n system of equations. For this, we have to use a solver such that we can obtain the vector u is equal to K inverse F. So now what do we have? Now we have these coefficients ui, u1 to, for our case, u5. These are obtained. Once I have these coefficients, then I know the finite element solution at every point in the domain. Once I know this, then what do I do with it? I am going to do a post-processing of the solution. That is, I am going to post-process the finite element solution to obtain what? I may be interested in displacements at a point, at a given point. I may be interested in the axial force at some other point, okay, so on. Or I may be interested in the stress at a point. This depends on what is really required out of the analysis. So once I post-process and I obtain these solution quantities, then I have to decide as an analyst whether what I have obtained is acceptable or not. If it is not acceptable, then we have to do refinements in our approximation. After the refinements have been done, then we repeat the same process of obtaining the solution, obtaining the coefficients ui, and post-processing our solution to get our response quantities of interest. Then we have to plot them. So plotting becomes a very important part of any finite element analysis we do. So the post-processor involves first extracting the quantities of interest and then plotting them in a way that is acceptable to the user. And in most commercial codes nowadays, most of the money is being spent in post-processing. So this is essentially the various steps that we are going to follow in any finite element analysis, be it for the analysis of the simple bar problem that we have taken, or the beam, or a plate, or a shell, or anything that we are interested in. So why do we need to use the finite element method? There are so many methods which are available to obtain approximate solutions to the boundary value problems that we encounter in engineering or mathematical physics. The answer is that in the finite element method, there are no constraints with respect to the domain boundary or the boundary conditions that can be handled. This is a very important advantage that we get when we use the finite element method, especially in 2 or 3 dimensional problems. In 1 dimension, pretty much all methods can give you the same efficiency, but in the 2 and 3 dimension problems, it really helps to do the analysis in a very efficient way, and also we can develop general purpose codes which can handle any given boundary condition or domain. So let us take this very complicated domain that I have drawn, which resembles a crazy potato made of different materials. For example, I may have material A in this region, material B in this region, material C here, material D here. This domain also has a crack at this point. It has a crack here. Then traction boundary conditions are applied here, here, which can be any type. It can be shear, it can be normal, or anything that we wish. And this potato is fixed at this end, while in this region it is resting on an elastic support. That is, it has spring boundary conditions. If I have to do the analysis of this problem, let us say that I would like to do a planar elasticity analysis, then most of the methods that are available to us will have a great amount of difficulty in doing a good job. With the finite element method, what we can do is we can very easily mesh the domain piece by piece. That is, each material domain or subdomain can be meshed separately. Then we can bring all those together, apply the boundary conditions as we have seen, and also take care of the crack, and we'll get a solution. We can make also modifications or improvements to the solution if and when desired by the analyst. Let us come to the third point. as I have shown in the figure, that one analysis may not be enough to get a good representation of the response quantities of interest. For example, in the case of the crack domain, I would like to have a special kind of a mesh or special approximations in order to capture the response quantities accurately. Accurately means they have to be within acceptable engineering tolerances. So convergence of the solution plays a very important role. That how do I improve my approximation? It turns out that the finite element method is based on a very sound mathematical background, using which we can decide how to improve or augment our approximations. From commercial point of view, a great advantage of the finite element method is that I can write one general purpose code or a program to handle a very large class of problems. That is, my program does not change if my boundary conditions are changing, or if my loading is changing, or if my domain is changing, material is changing. All these various changes can be handled by one program. So given these advantages of the finite element method, let us now look at some typical engineering analysis problems that may be of interest to us, which can be solved using the finite element method. For example, we have already looked at some of them, i.e. the extension of a bar, bending of a beam, torsion of cylinder members under static or dynamic loads. Or I may be interested in steady state or transient heat conduction problems. So if it is steady state, we are interested in a static problem, solving a static problem. When it's a transient heat conduction problem, then we are solving a dynamic problem. I may be interested in bending and planar deformations of plates and shells, which are very important from the point of view of analysis of pressure vessels and for aircraft wings, and various other structural members that go either in automobile engineering, aircraft engineering, or even in civil engineering. In many problems, especially with respect to thin or slender members, there is an issue of failure which has to be analyzed along with the typical material failure, which is buckling. So buckling of members, of slender members, is of great engineering importance from the point of view of designing of members. Buckling can be studied quite easily using the finite element method. We may be interested in analyzing flows, that is the fluid flow problem. For example, flow past a train. If it has to be analyzed, the finite element method can be used. Or I may be interested in finding out what happens to a cricket ball when it is delivered by a bowler. So in those cases, the approximate solutions, or what we call as numerical simulations, can be obtained using an appropriately designed finite element analysis. I may be interested in the acoustic problem. For example, the sound generated by exiting jet from a rocket, or the sonar waves that are sent by a destroyer to hunt down a submarine. So all those things can be analyzed using the finite element method. I may be interested in the vibration of continuous systems, again from a flutter point of view or from just a dynamic analysis point of view. I may be interested in knowing what happens to a structure when it is impacted by a projectile. This is very important in the current age of warfare, where we have to design bunkers which can withstand the sophisticated projectiles or bombs that are launched at them. Then I may be interested in the fatigue of structures, which is again very important in, for example, aircraft engineering, because an aircraft takes off, goes into a flight regime, lands, repeats the same cycle. So all the sorties are essentially repeating cycles, and under these repeated loads, the aircraft tends to fatigue. So fatigue failure can be analyzed using the finite element method. We know that most of the materials that we have do not have one predictable material property because of manufacturing defects, because of where I am getting the raw material from, what is the raw material. So a random analysis is often very useful. Also the effect of changing loads, changing geometries, everything can be incorporated, and for that also we can use finite element methods, and we have a special branch of finite element methods there called the stochastic finite element methods. Similarly, I can look at more complicated mathematical models corresponding to the behavior of structures under large loads, which are typically given by plasticity based models or viscoelasticity based models or viscoplastic models. These can all be studied using the finite element method. Now we have new materials, new structures which are coming up. For example, laminated composite plates and shells are used heavily in most fast moving vehicles, for example the light trains, the light cars, the race cars for example, and most of the aircrafts. Our ALH, which is the Advanced Light Helicopter that India has made, and LCA, the Light Combat Aircraft, are mostly composites based vehicles, air vehicles. So the analysis of laminated composites also becomes very important, and most of these places where these things are designed and manufactured use finite element analysis to give them the preliminary design. Another field which is of great importance as an emerging science and technology field is smart structures. Analysis of smart structures can again be done in a very routine way using the finite element method. Structural optimization, which is a key in designing better components, lightweight components, components which can carry the worst loads that the structure can bear without failing, that comes under the heading of structural optimization. All these problems can be analyzed using the finite element method, and it is being heavily used in the engineering industry. What we will do in the next lecture is we are going to develop the fundamentals of the finite element method and the finite element formulation using the simple bar problem that we have drawn earlier. Once we develop the basic framework and the structure, then we'll go ahead and look at the detailed analysis using the finite element method.